So we're looking at interference of light, but let's just quickly review because it actually is relevant and very similar. What happens with waves, let's say on a string or something like that, right? So you've got in this first case here, suppose you've got like a faster medium, right? So it's just sort of represented by a thinner rope here, and then you've got a slower medium. What happens once this wave pulse gets to the boundary here? Right. So this is just a drawing though of what you get, right? In the first case, you have a wave and a faster medium. It gets to the boundary here between the slower medium and the faster medium. So it gets reflected out of phase, as we say, but there's also a partially transmitted wave. I can show you the first part here. So this simulation here just represents like waves on a string or whatever, right? So we've got our string and it's just sort of showing all the, like trying to show the particles or whatever of the string. So you can, I think with this one, can I just do a pulse? Right. Let me just send one. That's what we're looking at here, right? So this is basically just Newton's third law when it gets to the fixed end. And this is sort of an extreme example of what we were looking at. If you go back to what we actually had here, it's like, well, if you have a fixed end, and so just sort of imagine that right here, this is completely fixed. It can't move up or down at all, right? Then it gets reflected out of phase, right? So it's a crest, it gets reflected as a trough. And what we're looking at when it's a slower medium is just sort of an in-between. The other, I don't know if it's like the other extreme, but the other side of this is, well, what if this here was just the same material, right? Then the pulse would just continue as is, right? And so you do get some of that here. This would be with a little bit of a reduced amplitude because it's, slower medium, but it still continues. But part of it, because of the fact that it's going into a different medium, part of this wave also gets reflected. And what if we have this other situation here? What if we have this thicker rope here, and then it goes into, so we could say it's in a slower medium and it goes into a faster medium. Then what can happen? I'll try to show you roughly what, again, I don't have, I can't show you the transmitted one on this, just the way this simulation is, but we can look at the reflected end. And this is an extreme example. So what we have a loose end here, or I just changed it so the end now is loose. It's not, we had a fixed end, right? It couldn't move before. Now we're looking at a loose end. So it can go up and down. And so you could sort of imagine the extreme case of this is we've got a really, 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 really light rope or string on the other side of this, right? That effectively doesn't matter to this. So let's see. Let's send a pulse. Whoa. Let's see it again. Right, and you can see that got reflected in phase, right? It was a crest, it got reflected as a crest, and that's basically just because the end can go up, right? If that end can go up, then it's basically like just sending the wave, like that energy just goes into the end, it goes up, and it basically sends the wave back the way that it came. I might sort of sketch it like this. And I would indicate here, again, if we're starting with this, and you can see sort of the direction of the wave indicated there, then I might indicate here that this wave is, right, this is reflected in phase. Right. And in both cases, right, you see the transmitted wave, if there is another material there, it's reflected in phase, right? It basically just keeps going through the material. We could look at this as some sort of form of refraction, just like we do with light, and where there may be some changes to it, particularly in terms of the wavelength or amplitude or whatever, but it is, it does go through in phase. It's really what we're looking at here is the reflected wave. And we're saying that, look, if you have a slower material like we did up here, then it's going to get reflected out of phase. Whereas if you have it going into a faster medium, it should get reflected in phase, right? It sort of acts like that loose end here somewhat, right? So if we look at something like light going into or trying to go into glass, we're seeing that, well, we already know there's going to be some refraction or whatever. So let me just draw right? We're going to have a refracted ray. But the main thing here, we're going to have a reflected ray. Angle looks more or less okay there. But what's really key here is that just like here when we're trying to go into a slower medium, this is going to be reflected out of phase. On the other hand, if we've got, say we've got light going through glass and then it hits a glass air medium, we're going to have a refracted ray. Right? Some of the light is going to get refracted. We can draw it like that. And we're also going to get a nice reflected ray. But in this case, it's going to be reflected in phase. Okay. And in this case, you can kind of, imagine like sort of the similarly, right? You can sort of imagine the extreme end. If something's going into a slower medium or whatever, right? It's just sort of that extreme case, right? Like where you're looking at something like a mirror where nothing gets reflected. So, but basically what you're looking at here, right? Here we're seeing it but it's a transverse wave. And remember, light is also a transverse wave, right? It's just, we're looking at an electric field, right? And so you're saying you've got some material down here that can resist that electric field, right? That they can offer you that resistance. If it's a more dense material with a higher index of refraction, then it basically acts like a fixed end in part, and it resists that electric field, and so it reflects it out of phase. And similarly here, if you got something that sort of works like a loose end, then it gets reflected in phase, right? It doesn't, it's really more the electric field can just sort of interact with itself, right? It can affect whatever, and I didn't even draw here, what's going to happen there. So it was like a loose end, if you will. What are the implications of this? Well, before I look at that, let me just remind you that when light enters a slower medium, the frequency remains constant. I think I mentioned that yesterday, but it's worth noting that it appears to slow down, and that's it's the speed slows down, but it's not the frequency that actually changes, right? The frequency remains constant, and so it's the wavelength that has to change. So if we look in a vacuum, if we look in a vacuum, we can say that right, C just equals F lambda. That's just the equation of V equals F lambda, and we can rearrange that for the frequency, which is the thing that's going to remain constant. So that means in any medium, we can express the speed in the medium as F, which is going to remain constant, times whatever the wavelength is going to have to be in that medium, right? So if it slows down, lambda is going to have to decrease. And then we can rearrange that for lambda, that is the wavelength, but since the frequency is constant, here, right, we can actually replace that with C over lambda, because that's also equal to the frequency, and we can end up with an equation here, right? So the lambda in any weight in any material is equal to, in this case, in the final one I've circled here, lambda is lambda in a vacuum, right? It's just the whatever that would be in going through, let's say, I hate to say empty space, it's not really like that, but we'll call it empty space in a vacuum. And NF is just the index of refraction in the material that it's going to go into, right? So in a material we're denoting F, it's going to have lambda F, and that's going to be equal to whatever lambda was in a vacuum divided by the index of refraction, which remember is going to be a number greater than 1, so it will reduce. So now we can actually look at interference in a thin film. I tried to get some pictures here because it's like, well, I want you to actually, you've seen this probably, right? This one on the bottom, which, just kind of like a really thin coat of oil or something like that on top of water. You've maybe seen something like that, or even soap and, really thin film of soap, right? Sometimes you get this weird sort of refraction phenomenon or whatever, and you see stuff like this. So what causes this? How can we predict this, if you will? And really, what we're interested in here is when we're going to get, when they're going to be in phase, right? When you've got some reflected ray here, let's say, and some of the light that gets refracted, but when it's going to join back up, when is this actually going to sort of add to the other one? When are you going to get something that's a little bit more intense, if you will? And that's going to be something that you'll kind of notice, right? You're like, oh wow, that red light or whatever that wavelength happens to be is more noticeable at this angle or something. So we've got air, and for this one we've got air, and the real thing to look at here is we've got an index of refraction of 1, and then it increases, and then if you've got glass at the bottom, it increases again. Right? So depending on whatever the indices of refraction are, again, it could be, so soap is our thin film here, but it could be, a really, really thin film of glass, and it could be soap or something on the other side. So you really have to pay attention to what sort of the order is of the indices of refraction. Are we going up and up again, or what? Because that's going to influence what's happening here at the boundaries in terms of the reflected rays. Okay, so let's, it's not really indicated here, so we'll just call this some thickness T. Right. And then we'll look at what actually happens. Now, it's worth noting when this phenomenon actually happens, like when you're seeing stuff like you do over here, the angle of incidence is actually really, really small. So this is exaggerated a little bit, like in reality. So I'll just put a note here. Is small. Right, so we're just sort of exaggerating this a little just so we can show some of the geometry or what's happening. So if we've got air and we're going into a slower medium, what happens to the reflected ray? This ray here is reflected. Was this in phase or out of phase? So remember, think of the free end or whatever, right? So, or this is sort of not the free end. This is like the fixed end, just not we're headed towards that, right? So this is going to be reflected out of phase. And what that effectively means, right? If whatever point in the wavelength this is at, right? It's sort of getting kicked right? It's getting kicked, like you could look at it as getting kicked back like a half wavelength or something like that, right? Now the part, remember the part that goes into the material, right, is unaffected. It just stays in whatever phase it's in. But in our example here, now yes, there would be some that would actually get refracted from the soap into the glass, right? But we're kind of ignoring that because it doesn't matter. What we're really interested here is what happens here, right? And this is actually the same, right? The same thing. We're looking at something that's going to get reflected. It's trying to go from soap to glass. So this is going to get reflected out of phase as well. And then if you follow this light that goes down here, after it goes up this way, right, it's going to go back into the air. So we know when it goes through, right, there's no out of phase real possibility here, right? So that means when it gets back, it's basically the same. So at the end of the day, what's kind of neat about this is we get a reflected ray here that's out of phase, and we get another one that's out of phase. So they both get kicked the same amount, if you will, or get adjusted the same amount when they reflect. So for all intents and purposes, right, it doesn't matter, right? If you make the same change to both waves, the net result is zero, right? So all we really need to know here, if we want to look at constructive interference, let's say, is we just need to know how thin is this thing in terms of wavelengths. I got ahead of myself and basically started writing all this thing out. So I said for the light that enters the film, right, the number of extra wavelengths, we can just denote that as n, is 2t over lambda f, right? So what we're looking at is how many extra wavelengths has the light that goes in here gone through, right? So it might go like that. It gets kicked out of phase, so it might come back the same way. But this here, right, this reflected ray also gets, kicked back, if you want to look at it that way, or forward out of phase. So as I said, that really doesn't matter. So how many extra wavelengths? Well, it's gone a distance of 2t, because I called this distance here t. So that's the distance. And then you just divide that by whatever the wavelength is in the film. So we're just denoting that as lambda f, to say that's lambda in the film, right? And so for constructive interference to occur, we're looking at n equaling 1, 2, like some whole number, right? Where it's gone an exact number of full wavelengths. And what that means then is that whatever phase this gets kicked back in, this one here would be in the exact same phase, right? So they're sort of amplifying each other, and you should see more of that light. And that's sort of what I indicated there. And then we can say, just take the equation we had here, and we can say, okay, well, then we already figured out on the last page, lambda f is just lambda over nf. And then take this equation here and multiply the top and bottom by nf, so that those cancel. And then we're left with n lambda over nf. Rearrange that, which I guess means divide both sides by nf, and we can figure out what that thickness needs to be to get constructive interference. And we end up with that. For destructive interference, right, we just need n, which is, again, n represents the number of extra wavelengths that the light wave that's gone into the thin film has gone through. So that just needs to equal a half, or 1 plus a half, or 2 plus a half, 3, right, etc., etc. And so all you got to do is replace the top of this thing here where we had lambda by a half lambda or 1 plus a half or whatever. So similar to what we did before, we're using M for destructive interference, and so we can say, well, in this case we just get an equation that's very similar to the last one. It's just got a half in there, so 1 minus a half, 2 minus a half, etc., and we end up with that right here. Now this all seems well and good, but the challenge is, as I mentioned, this was somewhat particular to this situation, right? We had the going from air to soap, which had a greater index of refraction, and then trying to go into glass, which also had a greater index of refraction than the soap. And so we could also have a situation like this, right, where we just have a thin soap film, and it's got air on both sides. Right? So if you do the math, basically what ends up happening here is you just flip these two equations. And the reason is, remember that this one here, let's say this wave here, gets reflected in phase, right? Or sorry, out of phase. But then this wave here gets reflected in phase. Right, so there's naturally a difference of 1/2 between the two, right? So if this distance was essentially 0, you're saying, well, this one here is reflected out of phase, so it's essentially, like, let's say, sent forward half a wavelength, right? So if this total was 1/2 wavelength, then they would actually be in phase. So now a half lambda or 1.5 lambda or 2.5 lambda actually represents they're in phase, versus this down in the bottom going some whole number multiple of lambda means when it gets out here, now they're out of phase, right? So as I said, the nice thing with that is all you really have to do, you can use the exact same equations. The only difference is going to be you're going to flip the order of them. So at the end of the day, you need to know two equations, or write down two equations. I wouldn't memorize them. I certainly haven't memorized them. But just remember what the situations are for, right? Because it's going to depend on what you actually have on both sides of the thin film. Okay, then. If you got the equations, give this a try, and then we'll take it out. But just to make a sketch of this thing here, right? A thin layer of glass, and we're given the index of refraction of the glass is on a transparent liquid, which actually has an index of refraction that's less than that. The glass is illuminated from above by light with a wavelength in air of 580 nanometers. I guess I might indicate that. Calculate the minimum thickness of the glass other than 0 capable of producing destructive interference in the reflected light, right? So we want destructive interference. And it's neat too, if you go back and look at refraction, right? You can see that, okay, this right here is refracted, and then it reflects off the liquid above, but then it gets refracted again when it comes out. And note that these are, right, have the same angle. Also note, remember, this actually happens in very, very small angles, right? But like we're really looking at something going almost straight down, and then, you know, like, but just to sort of look at what this looks like. So really the question is, for destructive, right? It's basically just which of those equations do we want, right? I actually try to write them down myself, right? Piece of paper here, and what I do is just kind of write down the first two that I have over here and say, okay, if no net difference, because that was really what happened here, right? Was we had one that was this got reflected out of phase, this got reflected out of phase, so there was no net difference. Then I say, okay, these are the two equations that I want, right? Whereas if there is a half lambda difference, then basically I just say flip the equations, right? So that's really what I want to look at here is I want to say, well, I've got the first one going from air to glass, right? So this one is reflected out of phase. And this one here, though, when it goes from, right, when I've got glass going to liquid, which has a smaller index of refraction, this is reflected in phase. So I'm dealing with a half lambda difference. So that means if I want destructive interference, I'm flipping these equations. So I look at the normal equation for constructive interference, which is that one here, and I'm good to go. Can I actually move this over here? So that means I'm looking at T, which is the thickness here, is lambda n divided by 2. Right. And I can basically, since the thickness is actually the thing that I want, I can pretty much just plug in the numbers here and say the thickness is equal to the wavelength, which is 580. It's nanometers, so that's times 10 to the negative 9. And I want the minimum thickness, so that means n equals 1. I might have put that in there, but and then divided by 2 and divided by the index of refraction of the film, which is the index of refraction of the glass, so that's 1.5. And that means that putting in those numbers, I get 1.93 times 10 to the negative 7. Is the minimum thickness I have, which is pretty thin, almost 0.2 micrometers. That's pretty small, right? That's like 2,000th of a millimeter. So that's a really, really thin film.